Okay, let's take a look at this problem here, Internal Revenue Service. A research center claims that at least 46% of U.S. adults think that the IRS is not aggressive enough in pursuing people who cheat on their taxes. In a random sample of 600 U.S. adults, 41% say that the IRS is not aggressive enough in pursuing people who cheat on their taxes. At alpha equal 0.01, is there enough evidence to reject the center's claim? Okay, so first let's write the claim as a mathematical statement. Okay, so here it is. A research center claims that at least 46%, so this is a claim about a proportion, and the at least means that its P is going to be greater than or equal to it. Okay, so my claim as a mathematical statement is P greater than or equal to 0.46. Okay, so this is the claim. Okay, so because the claim has the case of equality, the claim is the null hypothesis. So this makes the alternative hypothesis P less than 0.46. Okay, so this is going to be a lower tail test. Okay, so let's go ahead and check the assumptions to use the z-test for this, the proportion z-test. Okay, so remember in the text it states that if n times p is at least 5 and n times q is at least 5, then we can use the normal approximation to the binomial. So what that means for us is that we can go ahead and use that one proportion z-test in the calculator. Okay, so n in this problem was 600, and p is the claimed parameter. So basically I want to know, is 600 times 0.46 at least 5, and is 600 times 1 minus 0.46, is that at least 5? Okay, so this value, 600 times 0.46, is 276. Okay, so clearly that's at least 5. And this one here is 324, and that's also at least 5. Okay, so we can go ahead and use a z-test for this, the one proportion z-test in the calculator. Okay, so let's go ahead and calculate the standardized test statistic. Okay, that's going to be p hat minus p over the square root of p times q over n. Okay, so in this problem we know that n is equal to 600. All right, it says in the problem that in the random sample of 600 adults, 41% say that the IRS is not aggressive enough. So p hat in this problem is equal to 0.41. So plugging into the formula, our test statistic will be 0.41 minus 0.46 over 0.46 times 0.54 over 600. Okay, so let me go ahead and put that into the calculator real quick. Okay, so using parentheses in the numerator, I have 0.41 minus 0.46 divided by the square root of 0.46 times 0.54 divided by 600. Okay, so that standardized test statistic is about negative 2.457. Okay. All right, let's go ahead and compare that to a critical value. This is a lower tail test, so I'm just going to have one critical value. Okay, so I want to use a level of significance stated in the problem. It's 0.01. So I want to go ahead and find, either using the calculator or the standard normal table, the z-score that separates the lower 1% of the area from the upper 99%. Okay, so I'm going to go ahead and use my inverse norm function in the calculator. And because it's a lower tail test and the input into the inverse normal function is a cumulative area, I can go ahead and just put it in directly. Okay, so going to my distribution menu, I'm going to select 3 for inverse norm, cumulative area of 0.01. Okay, so I get a critical value of about negative 2.326. Okay, so now I want to compare where my test statistic lies with respect to the critical value. Okay, so clearly negative 2.457 is further in this rejection region. So I know that I'm going to be rejecting the null. Okay, but it's reasonably close to the critical value, so I'm going to expect my p-value to be reasonably close to 0.01. Okay, so that's my next step here, is I want to go ahead and use the p-value. Okay, so the p-value is going to be the probability of getting a test statistic at least as extreme as the one obtained by the sample. Okay, this is a single-tailed test, so I don't have to double the p-value. Okay, so I want to find the probability of getting a z-score less than negative 2.457. Okay, so I could use my normal CDF to get this in the calculator. I'll go to distribution, select 2. My lower bound is a really small number. If you have the older TI, you want to put like -1 and a string of 5 or 6 zeros here. My upper bound is negative 2.457. And I'm working with standard normal, so I don't have to change mu or sigma. Okay, so I get a p-value of approximately 0.007. Okay, I had expected this just based on the placement of where the test statistic is with respect to the critical value. Okay, it's further to the left of it, but it's reasonably close. Okay, so the p-value is definitely less than 0.01, but not by a whole lot. I mean, we are rejecting the null strongly here, but we have seen some smaller p-values in previous examples. Okay, so now let's go ahead and use the calculator to get the same output. Okay, so we're going to use the calculator now to get the standardized test statistic and p-value. Okay, so what I want to do is I want to press on my stat key, just like before. We're going to find all of our hypothesis tests under the test option, right arrow over tests, and I want to scroll down to the 1 proportion z-test. Either scroll down or select it, so I'll go ahead and select 5. Now I want to go ahead and put in the claimed parameter from the hypotheses. So in this problem it's 0.46. Now notice that the calculator wants the number of successes out of n trials. Okay, so we're going to have to calculate that. Now in the test statistic formula, we went ahead and put in p hat, okay, but the calculator needs x over n. Okay, so to remember the relationship, p hat is x over n, so p hat in this problem was 0.41, and the sample size was 600, so I could easily solve for x. So x will be equal to 0.41 times 600. Okay, so putting that into the calculator, I get 246. Okay, so going back to my 1 proportion z test, okay, remember I press stat, right arrow over to tests, and then option 5 on my calculator is the 1 proportion z test. Okay, again, I have my claimed parameter. Okay, I need to overwrite my number of successes. It's 246. This is just left over from a previous test. And my sample size was 600. And here I can change my alternative. Okay, this was a lower tailed test, so I need to select less than and then calculate. Okay, so you'll see that we get approximately the same standardized test statistic. By hand we got negative 2.457, and the p-value is really close. Okay, there was a little bit of rounding involved. Okay, we came up with 0.007, but here if we round to the nearest thousandth, we would get the same thing. Okay, so perfectly acceptable to use the 1 proportion z test in the calculator. Okay, so the conclusion at this point in time is that we are going to be rejecting the null, and the question is there enough evidence to reject the center's claim? So let's go back to our null and our alternative. The claim was the null hypothesis. So we are rejecting the null. So there is enough evidence to reject the center's claim. Okay, so we are rejecting the null, and in this case we are rejecting the claim. So to answer the question, there is enough evidence to reject the center's claim. Okay, and then I can include that at least 46%, etc., etc., etc. So I'd want to go ahead and restate that in plain English. Okay, so because we rejected the null hypothesis, it is possible a type 1 error may have occurred. Okay, just like before, this interpretation is the same. Because we are rejecting the null and we're doing this based on a sample, it is possible that an error was made. Okay, the errors are not intentional, it's just a byproduct of using samples to make inferences or test claims. Okay, so a type 1 error may have occurred since we rejected the null hypothesis. Last but not least, we can go ahead and calculate a 99% confidence interval. Since alpha was equal to 0.01, we want to find a 99% confidence interval for P. Okay, so I could go ahead and use the calculator for that. I could go to stat, right arrow over to tests, and I want to go to the 1 proportion z interval. There it is. If you keep scrolling down, you'll be able to find it. Okay, so it should carry over the information from the hypothesis test. Okay, the number of successes was 246, n was 600. I do need to change that level of confidence. Okay, so my confidence interval limits go from about 0.358 up to about 0.462. Okay, so is this consistent with rejecting the null? Okay, so let's go ahead and look at our hypotheses again. Okay, the alternative hypothesis was that P was less than 0.46. If we look at the confidence interval, most of it is below 0.46. Okay, so we have a smidge of covering here, but that's reflected by the fact that our test statistic was reasonably close to the critical value. Okay, but this is consistent with being in favor of the alternative.